Start recording. Okay. Yeah. So the first method, the Lagrangian method, you concentrate on a single fluid particle and you study its velocity and its acceleration. So velocity, from the definition of from physics, we know that velocity is the rate of change of distance with respect to time. That's velocity. It is a vector quantity. It has got distance. It has got size and direction. That is velocity, the rate of change of distance with respect to time. Then acceleration is the rate of change of velocity with respect to time. So now let us consider a particle in a space xyz, an xy plane, a 3D plane. And in a 3D plane, we have a particle with coordinates a, b, c, okay, which are functions of the coordinate along the x, the coordinate along the y, and the coordinate along the z, plus the time. Because for a particle to exist, it has to exist in space, and there has to be time. That time has to be there for something to exist. Space and time. I think for those who believe in God, we usually talk about God is out of space and does not depend on space and does not depend on time. Okay, and everything created, which is matter, depends on space, which is the first three components, 1, 2, 3, and also time. Okay, for something to exist, there has to be space and also time. When space, what it occupies, and time, when it began to exist, there has to be time. So given a fluid particle, depending on these coordinates x, y, z, depending on also on space and time, we can find the velocity components of that particle by finding the rate of change of displacement, the change in the x direction with respect to the change in time. So this is the velocity of the fluid particle as it moves along the x direction. Then v is the velocity of the same fluid particle as it moves in the y direction. And w is the velocity of the same fluid particle as it moves along the z direction with respect to time. When something is moving, let's say for example, when a bird is flying, okay, as it is flying, if it is flying, let's say straight along the x direction, there's a possibility that it will be blown by the wind and it will tilt a bit along the y direction. There's also a possibility that it can go up and down as it flies, that is along the z direction. So the same can be thought about when it comes to a fluid particle. As it is moving along the fluid body, it can be moving a little bit along the x-axis, and a little bit along the y-axis, and a little bit along the z direction, that is moving up and down along the x and along the y. Then the acceleration component of the fluid particle. As we said, acceleration is the rate of change of velocity with respect to time. Or you differentiate the displacement or the distance twice. Okay? Because we're differentiating u with respect to time. So now this is where it gets tricky. When I'm talking about differentiation and differentiation just in general, what do you know about differentiation? Let me hear feedback. Do you have any idea about this differentiation? When I say differentiation, have you ever seen anything being differentiated, any equation being differentiated or not? Yes, class feedback. Yes. Should I start pointing? You can just say something. When you hear the word differentiation, of an equation of a function. Do you have an idea what that means? Okay, I'll take the silence to mean that you have the idea.
Hello.
Hello?
Yeah, in mathematics, differentiation means parallel. But
Parallel?
in other subjects, if they say differentiate or differentiation, you are explaining the similarities or the difference between two different things or more different things.
Okay. Okay. So now let me explain these symbols here. This delta here, okay? This lowercase delta here. It means the change along the x, okay? The change. So if you have, let's say, x1 and x2, so this simply means x2 minus x1, the difference between 2 points along the x-axis. This is what this symbol means, this delta here. The difference between 2 points along the x-axis. Now, the delta here on time, it means the difference between 2 points in time. Okay, the difference between, let's say, 7:30 p.m. and 7:50 p.m. That difference, 7:30 p.m. and 7:50 p.m., which is what? 20, isn't it? So this is what this means. The difference between 2 points in time. So when you find the difference between 2 points in space and the difference between 2 points in time, what you get is the velocity along that direction, okay, or along that space. When you're finding the speed of a vehicle, okay, we observe, like, from the point where it is starting from to the point where you stop your observation. You compare we compare the distance it has covered from that point to the end. Okay, so usually we take the distance where the vehicle is starting at 0 and where it is ending, let's say 100 meters. So it will be 100 meters minus 0 over the time which took for it to move from the point where it started to the point where it ended. So if it took 10 seconds, so you say 100 meters minus 0 over the initial time was 0. So you're going to say, and the final time was 10 seconds. So you're going to say 10 seconds minus the initial time is 0. So you end up with 100 over 10, of which 100 over 10 is equal to just a 10. So you're going to say this vehicle is moving at a speed of 10 meters per second. So that's the same concept which is working here. Okay, that is the speed of a vehicle. Velocity is just speed, but a vector quantity, which means it has got direction and size. So now, for acceleration, you do the same thing. Now, instead of using distance, you use the velocity. So the velocity, the rate of change over. So this means that you are changing this one, okay? The velocity with respect to time to get the acceleration. So now, for you to find the resultant velocity and the resultant acceleration of a moving fluid particle, you square the velocity components like this: u squared plus v squared plus w squared, then everything under a square root. For acceleration, you square the acceleration components: a squared, ax squared, ay squared plus az squared, everything square root. So know these formulas: formula 1 and formula 2. Formula 1 is for the velocity, the resultant velocity. Formula 2 is for the resultant acceleration. Okay. Next, the disadvantages of the Lagrangian method. So what are the disadvantages of this method, Lagrangian method? The first one is that since you are looking at a single fluid particle, for you to study the entire fluid body, it becomes very difficult to track each and every fluid particle, so it becomes cumbersome and it becomes complex. And the equations of motion becomes very difficult to solve and hard to understand. So it just becomes so sophisticated. That is a disadvantage of using the Lagrangian method to describe the fluid flow. Okay, so when I ask what is the disadvantage of the Lagrangian method to describe the fluid flow, this is the disadvantage. It is complex and the equations becomes difficult to solve. The next method is a Eulerian method. Okay, this is now a commonly used method to describe the fluid flow. The Eulerian method. So in a Eulerian method, you still study the acceleration and the fluid velocity, but only that you look at a point in a fluid system. You look at a point in a fluid system. So instead of looking at a particle, you look at a point in the fluid system. Or you choose your own section you're going to observe within the fluid system. And then the components, okay, of velocity for a fluid being observed using the eye of Euler. These are the velocity components. They are dependent on space as well and on time. Dependent on space and time. Like that. So for you to find the acceleration components, you differentiate each velocity component with respect to time. So differentiating the first with respect to the variables, not to time, the variables. The variables here we have x is changing, y is changing, z is changing, and time is changing. So differentiate this u, you're going to have du. Okay, change in u, change of the velocity component along the x-axis will be given by the slight change, this partial du, partial dx, okay, means that the slight change of velocity component along the x-axis times the change in that space, small change in space, plus the slight change of this velocity along the y-axis times the change in the y space. You continue like that and you reach the change in the velocity component with respect to time times the change in time. So when you have this, then you divide the entire equation by dt, which is the change in time, dt. dt means the change in time from one point in time to another point in time. When you do that, so this is supposed to be dy du dx. This is supposed to be t, not x, okay? Take note of that. This dx is wrong. It's supposed to be dt, because we're dividing this equation throughout by dt. So when you divide this term by dt, the dt goes, because dt over dt is 1. So the dt here goes. When you divide this equation by dt, you're going to have dz dt. When you divide this term by dt, you're going to have dy dt. Divide this term by dt, you're going to have dx dt. Divide this term by dt, you should have du dt. Okay, there's a mistake here. This is supposed to be a t. So this implies that the dx dt, which is the change in space with respect to the change in time, is simply the velocity along the x-axis. Because velocity is the rate of change over this distance, or the change in distance over the change in time. The dy is simply the velocity along the y-axis, and the dz is simply the velocity along the z-axis. So when you have this equation 7, okay, these equations in 7, then you substitute them in equation 6. So on dx dt we're going to put u, on dy dt we're going to put v, and on dz dt we're going to put w. When you do that, this is what you get. This is for the velocity component along the x-axis only. This is the velocity component along the x-axis only. So in the same manner, you can calculate the velocity. I'm saying the velocity component. This is the acceleration component along the x-axis only. This is the acceleration component along the x-axis only. So in a similar way, you can find the acceleration along the y component, along the y-axis, and the acceleration component along the z-axis. So before we go to types of flow, any questions from the mathematics we have discussed there? Any worries, any questions, any concerns, any feelings about the equations and what they're trying to describe and what they mean in the yes, you can go ahead.
Yes, no, mine is a request.
Yes.
I see your module has got a lot of calculations, and unfortunately,
Mm.
as for me, I don't have this module, and also
Oh,
it might need some revision. So I don't know how the best now, because we can't access the portal, and it's maybe because some of us or others, they are not yet fully paid for the fees. So I don't know how the best you can assist us on this one.
okay. I can share these notes, but the thing is that those who haven't paid, there will be a time when I'll require you to write a quiz. Okay? And the only way I can administer a quiz to you is through the platform, the Moodle platform. So for those who haven't paid yet, please you need to pay as soon as possible so that as I give out the quiz, everyone is moving at the same time. Let me tell you, if you lag behind, that's how you don't want to be behind. Move with everyone. That way things will be better for you. So for now, I can give you the notes through WhatsApp. But when it comes to the quiz, there's no other way of giving you the quiz apart from the model. Yeah. Okay. So Eulerian method. Let's go to the class is only supposed to be for an
So,
hour. Yes.
yes, I'm trying to assimilate what we're learning. So now I'm looking at this slide. So we're talking about the studying of a particle in fluid at a particular moment. And then we've got
Mm,
these equations like U is equal to F1 what.
mm,
So if I'm getting this correctly,
yes.
so we're trying to find for U. So the U, this is the particle at these different moments. Or am I wrong? I think that's where I'm a bit behind.
You're talking about equation 8.
Sorry?
Are you talking about equation 8?
Let me just take you back to, I don't know, this is page where I was just started a Lagrangian method there. Yeah, that right there. So we've got these equations. I don't know. Yeah, the way I say U is equal to F what X. So the U is standing for a particle that we want to study in that motion. Am I right? And then the X Y Z, this
Mm.
is the moment in time where that particular particle is.
Yeah, the space
Or
and because when you say the moment, you're talking about time, eh? So the
or
x,
the
yeah. So we're saying u, okay? U is equal to f1 x, y, z, and t. So we're saying the velocity of this particle of this of the fluid we're observing is a function of the three space coordinates x, y, and z because it has to be in space for us to observe it. And then for us to make an observation, there has to be time. That is a t that we have there. Okay, x, y, z, and then t for the time. So the velocity is dependent on the space and the time. Okay, is that how is that?
Okay, I'm following now.
Yeah. So these are velocity components now. So if you can find the velocity, you can also find the acceleration, because the acceleration is just simply the rate of change of velocity with respect to time. So now we were writing this velocity components, and then we were supposed to go to types of flows or types of flow. So the flows, basically we have the steady and unsteady flows, uniform, non-uniform, 1, 2, or 3-dimensional flows, a 1-dimensional flow, a 2-dimensional flow, a 3-dimensional flow. We have rotational and rotational flows. We have laminar and turbulent flows. We have compressible and incompressible flows. So let's discuss each one of them. So what is a steady flow? So in a steady flow, the flow variables like the velocity and the acceleration or even the density of the fluid, okay, they do not change with respect to time. It's like water is flowing in a pipe. You come at different times, you find the velocity is the same. Okay, you come at 16 hours, the velocity is the same. You come at 17 hours, the velocity of the water that is flowing in the pipe remains the same. You find the density is the same. Okay, so the velocities, the flow variables such as velocity, the pressure of the fluid, the density of the fluid do not change with respect to time. Even the acceleration itself doesn't change with respect to time. So such a flow is called a steady flow. In an unsteady flow, the velocity, the fluid variables, or the flow variables, sorry, they change with respect to time at different instances. You find that the density is different, the pressure is different, even the velocity of the fluid itself is different. Such kind of flows are known as unsteady flows, and these are quite common. Okay, they are usually found in nature, these kind of flows. The uniform and non-uniform flows. So in a uniform flow, we now talk about space. Okay, that the velocity components, the flow variables do not change with respect to the space. Okay, so for example, when water is flowing through a pipe, okay, and at the end of the pipe, like the pipes that you use for what do you call them? The hose pipe, okay? The hose pipe has got a nozzle. When the fluid or when the water is flowing along that pipe, when it reaches the nozzle, what happens? The velocity of the fluid changes. Okay? It has changed because the shape of the pipe has changed. So even the velocity itself has changed. And it has changed because of the space it is occupying. So it has changed with respect to space. So such kind of flows that do not change, okay, the uniform, do not change with respect to space, they are called uniform flows. But when they change with respect to space, like the one I've just described, the flow of the fluid of water from the pipe to the nozzle, okay, there's a change in velocity there. It accelerates actually. Such kind of flows are known as non-uniform flows that changes with respect to space. So when I ask what is a uniform flow, differentiate a uniform flow from a non-uniform flow, you're supposed to think about space to say, okay, in a uniform flow, the velocity changes with respect to, it doesn't change with respect to space, and in a non-uniform flow, the velocity changes with respect to space, the space it is occupying. Then we have rotation and irrotation flows. In a rotational flow, the fluid particles, while moving in a particular direction, rotates about the center of mass, or the mass center. But in an irrotational flow, the fluid does not rotate in any direction. We also have laminar and turbulent flow. So in a laminar flow, the fluid particles flows in a straight line, okay? And some of the examples of laminar flows are flow through a capillary tube. A capillary tube, an example is a straw. The straw that we use when you're drinking cocktail, you're drinking which other drink, of whatever drink, but those straws that we use, when the drink is flowing along that straw, it flows in a straight line, okay? It doesn't crisscross. The fluid particles maintains the position as they move up the straw. Another example is groundwater flow and flow of blood through the veins and arteries. Although the arteries, they say the aorta, which is the biggest artery, there is turbulent flow. So in turbulent flow, the fluid particles flow in a zigzag manner. An example we can use to differentiate between a laminar flow and a turbulent flow is this. In a laminar flow, the fluid particles moves in a straight line, they don't crisscross. Okay, but in a turbulent flow, they move in a zigzag manner. They are not straight. Okay. Another flow is compressible and incompressible flows. So in a compressible flow, the density of the fluid changes from one point to another. When you look at the brake fluid which is used in vehicles, one of the reasons why they choose that particular fluid is that when you apply pressure, okay, in that tube as you try to brake, that fluid we can assume that it does not compress, okay, because if it compresses, it will delay the response of the vehicle, because it has to compress first. After it is compressed, that's when the pressure now goes to the brake pads. Otherwise, if it is not compressible, the moment you just step on the vehicle, the effect will be almost instantaneous, to be almost instant. And that's why that fluid is mostly used, because it is not compressible, theoretically. So such fluids which are not compressible are known as incompressible fluids, and flows in which an incompressible fluid is involved are known as incompressible flows. Before we do an example, any questions on the types of flows? Any questions before we do any example? Questions on types of flow? Any questions on the types of flow? Any questions, class? Are you eating or what? What's happening? No one. Are you in class? Because these online classes, people are busy. People are usually busy doing something else, and then you'll be talking to yourself.
No, we are there.
Augustine. People usually, these online classes, people they usually do other things as you try to explain what is happening. So let's do an example. Okay. So in a fluid, the velocity field is given by that equation. V is equal to 3x plus 2y I plus 3z plus 3xj. So the i's and the j's are representing the vector or the direction of these components. So I generally represents the x-axis, j represents the y-axis, and k generally represents the z-axis. So this is like v with the components along the x-axis despite having a y here, components along the the y, and these components along the z-axis. Then they're saying determine the velocity components u, v, w at any point in the fluid field, in the flow field. So determine the velocity component. So from the I, j, and k, you should think of this as this is the velocity component along the x-axis, the velocity component along the y-axis, and this 2t minus 3z is the velocity component along the z-axis. Then so you say we are going to get your u, okay, which is the velocity component along the x, will be equal to this equation inside 3x plus 2y, and your v 2z plus 2x, and your w 2t minus 3z. These are the velocity components. That's how you pick them from the velocity field. The next question is saying determine the speed at point 1, 1, 1. So they're saying find the speed when x is 1, when y is 1, and when z is 1. So how do you find the speed? The speed is a resultant velocity. Excuse me. And remember the formula for the resultant velocity?
Sorry, sir.
Yes.
I think just start again, sir.
On which
I'm a bit
one?
behind. Just, don't mind. Just start again on the explaining on the example. Just starting from the equation. Well, I missed you where what the S and the K's. I don't know if you said they stand for the view U W. I don't something like that. My
Okay.
network was tripping.
Yeah, so the I, J, and K, these they show you the direction, whether it is along the X, Y, and Z. So the I is generally stands for the X direction, whatever is happening along the X direction. In this case, we're talking about velocity field. So we're talking about the velocity along the X direction. The J stands for whatever is happening along the y direction. So in this case, we're talking about the velocity. So this equation 2z plus 3xj is representing the velocity along the y direction, and the k, of course, describes the velocity along the z direction. So in the question, when they ask to say find the velocity component, you just pick because they have been arranged already for you. Okay, the I have been pushed together, the J's have been pushed together, and the K's have been pushed together. So you just pick them, just unpick them the way they appear. So this one for the I is the velocity along the y direction. This is the first velocity component. The J is the velocity component along the y direction, and the 2t minus z is the velocity component along the z direction, which is represented by w. Okay, the next question is saying find the speed at the point 1, 1, 1. Remember, this velocity has got three components or three coordinates, x, y, and z. So in this case, the x is 1, the y is 1, and the z is 1. So you just substitute, but remember the speed is a resultant velocity. Speed is a resultant velocity, which is given by you square the velocity component plus you square the velocity component along the y plus you square the velocity component along the z, and then substitute in which one of them. Put a 1 on x and a 1 on y, put a 1 on z and a 1 on z. on x. Put the t has not been given. Okay, we don't know the value of t according to question number 2. We don't know the value of t, so we're not going to put anything there. But on z minus 3z, we're going to put a 1 on z, and then square each and every one of them. Square each and every one of them. You end up with this equation under this root: 4t squared minus 12t plus 59. Okay, when you make those substitutions, so you should go through after the class. You should find time to go through on how this speed was found for x is 1, y is 1, and z is 1. T wasn't given. So this is the speed for these coordinates. The next question says, finally, determine the speed at t is equal to 2 seconds at point 0, 0, 2. So at this point, when x is 0, when y is 0, and z is 2, find the speed, and the time must be given to be 2 seconds. Also clarify the velocity field as steady, or classify the velocity field as steady or unsteady, uniform or non-uniform, and 1, 2, or a 3-dimensional flow, whether it is a uniform flow, non-uniform flow, steady or unsteady flow. When we've done this substitution. So first thing, you're substituting. You're going to substitute on x, you put 0, on y 0, on z you put 2. So when you do those substitutions, you find that your u will be 0, your v will be 4, and your w is going to be negative 2. Then you square each one of them to find the velocity. Okay, because velocity, resultant velocity or speed, you're squaring each velocity component, then you sum them. So the first one is 0 squared, the second one is 4 squared, the third one is 2 squared. You find that you end up with the square root of 20. Okay, 20 units. 20 units. Now you found the speed. So now they're saying classify whether it is uniform or not, whether steady or not, whether it's 3-dimensional or not. So the first classification for the unsteady or steady, remember we said that it is a flow is steady when it is dependent on time, otherwise it is unsteady. So since v at given space depends on time, it is unsteady. It is unsteady. The next one we are going to is whether it is uniform or non-uniform. So for steady, it is time. For uniformity, it is space. Since at given time t, the velocity changes in the x direction, or whatever I wrote here, since at given t, velocity changes in the x direction, it is a uniform flow. Okay, so it is uniform flow because the velocity, because this velocity is dependent on space. Okay, sorry, it is non-uniform because it is dependent on space. Here I just specified one space coordinate, but you can say since it is dependent on the space coordinates, which is x, y, z, then it is non-uniform. Then for the dimensions, whether it is a 1-dimensional flow, a 2-dimensional flow, a 3-dimensional flow, we have free space coordinates upon which this flow is dependent. So therefore it is a 3-dimensional flow. You have x, y, and z, and therefore implies that it is a 3-dimensional flow. Then you would have classified whether it is uniform, non-uniform, steady, unsteady, or 1, 2, or 3-dimensional flow. Any questions on the example before we do another example? Any questions on the example before we go into another one? Is it clear or it is confusing or you're still digesting? I know this is the hard part because mostly people are not comfortable with the mathematics, but even these can be mastered as well. Yes, go ahead.
Yes, sir. Since you are recording, we'll go through the record again, and I believe we'll be able to understand.
Oh yeah. Mm. Okay, let's do the next example. In the next example, we've been given the velocity as v is equal to 2t, then we have 1 minus x over 2l close bracket squared, where v is the velocity, t is time, x is distance, and l has been given to be 1 point. Oh, sorry, this is the question. The question is saying calculate the local acceleration, calculate the convective acceleration, and then calculate the total acceleration. Okay, given the velocity equation here. But remember what we said. We said acceleration is the rate of change of velocity with respect to time or to space. It can be time or space, because velocity can change with respect to time and with respect to space as well. So now the first local acceleration. So local acceleration is the I wanted to say the normal acceleration. It's like the common acceleration, which is the rate of change of velocity with respect to time. That is our local acceleration. So find the change over velocity with respect to time. So differentiate the given equation. Okay, this one with respect to t. We are going to reduce the way you differentiate equations is that you reduce the power and multiply the coefficient. So the power t is to the power 1 here. We're going to reduce the 1 minus 1. Then the power which was there times the coefficient of t. The power of t here is 1. So to be 1 times 2, to be a 2. And then the t here will reduce in power from 1 to 0, which is going to be 2 to the t to the power 0. And any number to the power 0 except 0 is always a 1. That's why we have 2 times, there's nothing here, there's a 1. Times now what was given in the brackets. Then after that you substitute, okay? Substitute the given values, these values here. X is 1 and the L is 1.6 meters. Substitute them here. X is 1, L 1 point, I don't know why I put 1.5. It's supposed to be 1.6 meters. And then evaluate this. You should get 0.945 meters per second squared. Meters square per second squared. So this is the acceleration, the local acceleration, which is the acceleration as the velocity component as the velocity changes with time. For the convective acceleration, the formula is given by this: v times the rate of change of velocity with respect to time, which is v, the given velocity, 2t 1 minus x over 2l squared, times differentiate the given equation, this one, with respect to x, find the derivative. When you find the derivative of that, this is what you get. You get 2t times 2 1 minus x over 2l times minus x over 2l. Then substitute your x is 1.6, your x is 1, sorry, your a is 1.6, when you and your t is 6 seconds. When you substitute that, you're going to get negative 29.24 meters square per second. Meters per second square. Then the total acceleration is equal to the local acceleration, the one that we found here, plus the convective acceleration, this is the one that we found here. So add the two, you end up with a total acceleration which is negative 28.295 meters per second, which means that this fluid particle or this fluid body was decelerating or was reducing in acceleration because the value is negative here. So any questions? This is the end of our class. Questions on these examples or generally on the class, on the way forward, on how we're going to move and survive when we get through this class. Any questions? Class?
We need some revisions on this differentiation thing. So
Yeah.
that dvt, yeah, and also dvdx, because the way you calculate your figures, yeah, it's been a long time, but I think we'll catch up also if we do more revisions on differentiation.
Yeah. Yeah, differentiation, you need to revise that. Because all the fluids, as they flow, they are governed by differential equations. We use differential equations to describe them. So there's no way we can avoid these differential equations. Yeah. So in the next class, we are going to discuss the rate of flow or discharge as the fluid flows through a pipe. Okay, we can talk about water in a hose pipe as it flows and as it comes out of the nozzle. That is the discharge. At what rate is it flowing? At what velocity? How does the area of the pipe or of the hose pipe affects the velocity, affects the discharge, and affects the flow in general? So that will be a discussion for our next class. For today, we're done, and I would want these classes to be short as possible, maybe within an hour. Like, it shouldn't take more than an hour to do these classes. Then for the assignments and quizzes, I won't be ambushing you. I'll be letting you know in time to say we're going to have a quiz for 10 minutes at what time. But remember, there will be those who will only be done on Moodle. So if you haven't paid, try to work on that. Okay? See you in the next class, and let's see if there is any questions.
Yes, sir, there's a question. Are you going to send after the class the video or?
I think the video I'm going to send tomorrow.
Very well noted.
Thank you so much. When is our next class?
Our next class is going to be on Monday. So we're supposed to be having classes on Mondays and Tuesdays. So our next class is Monday. If I forget, please remind me, because these classes we usually have them after I'm done with the normal week. So I'm usually tired and I want to go home, so I usually forget about your class. So you can remind me on Monday or Sunday. Start tomorrow. We're having class. Okay, on Monday, Saturday we're having a class. Yes, so that I can prepare in advance. All right, class. See you next week.
Thank you, sir.